Okay, great. Yeah, well, why don't we get started then? So it's really our absolute pleasure today to have Richard Zhang present for us. And so he'll be presenting on, as you'll see in front of you, learning to generate models of 3D shapes. From implicit functions to structured representations. And so, Richard, we know very well as a neighbor at Simon Fraser University, where he is a professor in the School of Computing Science. And he actually holds a distinguished university professorship there currently. He's also been visiting professor at Stanford, Shenzhen, and Beijing Film Academy as well. And so Richard directs the Groovy, which is graphics and vision lab at Simon Fraser University. With interests in geometric modeling, shape analysis, 3D vision, geometric deep learning, and also computational design and fabrication. And yeah, so particularly any work that really lies at the intersection of geometry and machine learning. Richard's group has really been pioneering the way for many of these methods. He's been, he has a Google Faculty Research Award and a variety of other awards, including Applied Science Research Excellence Award at SFU, and also National Science Foundation of China Overseas Outstanding Young Researcher Award in 2015. So with that, let's get started on the talk. And so do feel free to post questions in chat. I'll try to do my best to feed those to Richard as they come up. So welcome, and take it away, Richard.
Thank you very much, Michael. Can you hear me all right? And the slide is transitioning?
Yeah, looks good.
All right. Good. Yeah. So my talk is going to be about generative models. So these are models that describe some kind of a rules or data distribution, so that you're able to generate new data. Maybe it's a new image or new 3D shapes. I guess everyone has their own favorite generative models. Some people like graphics, graphical models, and now with deep learning, autoencoders and GANs are both primary examples of generative models. So why should we care about generative models? I guess there probably are many possible answers. What I want to first is to make a point that I believe that learning to generate actually lies at the very heart of AI. So if you think of AI, one of the most prominent questions is when does a machine become human? So everyone knows the famous Turing test, which is a test of the machine's ability to make human-like conversation. And by and large, the test was regarded as having been passed in 2014. So is this test too easy then? So a much lesser known test is actually called the Lovelace test, attributing to Ada Lovelace, which is usually regarded as the very first computer programmer in the world. And this test is actually about the machine's ability to be creative, to be able to generate something which is original. Maybe it's a poem, or it's a shape, or maybe it's a logo. So it's a lesser known test, but many believe that this is actually better AI detector. The point here then is what really separates humans from machines is not the ability to make a conversation which lacks a human, but it's actually the creativity, human creativity, to the ability to be original. The example that I show you here, this logo design, there was actually a side project I had probably from a few years ago. We actually tried to develop a machine that is able to generate logos like this, which is actually very creative, but it turned out to be a very difficult problem, and then we actually went nowhere. So this talk is actually not going to be about creative modeling, so we're going to take a step back. So we want to generate without requiring creativity. So it's kind of a playing an imitation game. We're going to learn from examples without being original. And the goal here is to generate shapes that are plausible, have good quality in terms of realism, and also have diversity. So now deep learning is so popular and has made so many advances. In particular, there have been a lot of recent success on synthesizing speech, faces, or natural images. So here's just some of the examples. They are not even the the state-of-the-art results that show amazing results on image generation. Now, in contrast, these are some of the best methods that are able to generate 3D shapes, either from a single image, essentially it's a single reconstruction, or like a GAN that are able to generate 3D shapes. If you look at the kind of detailed quality, is certainly far behind image generation. So first, I want to highlight some of the unique challenges that we have to face when training deep neural networks for 3D shape generation and reconstruction. So the first one is probably an obvious one, the 3D data challenge. Right? So in order to perform deep learning, we need lots of data, right? Either acquisition or interaction in terms of labeling 3D data, it becomes much more difficult compared to image or sound waves. So we're still kind of lacking a big 3D data to train deep neural networks for many of the analysis and the synthesis tasks. And the second challenge may be something that not everyone is aware of. I will call it the affordance and functionality challenge. So let's ask ourselves, why would we want to design and generate a 3D object? I would say certainly not just to look at it, right? So we design something, either it's a 3D object or it's a 3D environment. I believe the purpose is actually to use it. So certainly it's not enough for this 3D object to just look right from one particular angle, where it's actually not even a connected 3D shape in this example. And it's not just about what it is, just like, if you're able to use a CNN to recognize it, so which it would do if you have just the right parts, and the parts may not even be in the right places, then the CNN may still say it's a face or it's a teapot. So that's not enough. So what I believe is that what really matters is to generate something, and for that to be able to afford to be able to function. So it's actually about what it can do and can afford. So to me, I think the ultimate goal to generate 3D objects or scenes is not appearance, but functionality. The generated 3D scenes and shapes need to function properly. So although this talk is not going to be about functionality, but I'm going to spend a few slides just on this very topic because I think it's actually very important. So learning functionality is challenging because functionality is something which is contextual. It is not sufficient just to take an object and then try to learn its functionality. You actually need to see the usage scenario. And that usage scenario is provided by some kind of interaction between the object in question and other objects. For example, the agents, it could be a human hand, like holding a badminton racket, or it can be humans, right? Riding a bicycle, or it could be other objects like the coat hanger interacting with this cloth. Now, if you have to deal with interaction context, then everything is harder, right? It's harder to collect such data, it's harder to describe interaction context, and it's difficult to generate these kind of interaction situations. And if you think there are not enough 3D data, even there's less 3D data with functionality annotations. And if you think of defining some kind of a deep neural network that can produce something which is functional, then you have to think of some notion of what is a differentiable functionality law. So these all are challenging questions to answer. So the good thing is that it's indeed an intriguing and emerging topic in fields like computer vision and graphics and machine learning as well. So here's just some of the samples of works. One thing that's very relevant to my talk is that functionality of a 3D object is typically characterized by the functionality of the parts, and in particular, also part relations. So here's a very simple example to show you. On the left, you have something which is functional. On the right, you have something which is not functional. And this functionality is entirely defined by the angles that are made between the parts in this chair. So part relations is very important for studying and learning functionality. Okay, so going back to my third challenge, which is I think is the most fundamental challenge, I call it the representation challenge. Unlike images with speech, for 3D shapes, there's really not a universally accepted representation. You can say that this is the representation for 3D shapes. No, we don't really have that. On the low end representation, low-level representations, you have some people who like meshes. I mean, if you're in graphics, meshes and volumes. And now recently, there has been a lot of works on point clouds being the representation for geometric deep learning. And this is just low-level representation. And if you go for higher level representation, you have CSG, which stands for constructed solid geometry, represents a 3D shape using operations between geometric primitives. You also have structural representations that have a set of parts. And finally, last but not the least, you have multi-view representations where a 3D shape is represented by taking photographs from different angles. So actually, for each one of these representations, I can probably point out to 10, 20, 30 or more papers on how to design a neural network to learn something, right? But most of these networks actually were developed for discriminative analysis, right? Much fewer of these methods were developed or were suitable for 3D shape generation. However, the study of deep generative models have been an emerging topic for a while now. Now, certainly the first attempt is trying to build on the success of image generation and think of what is the most natural generalization or extension from that. And the answer would be voxel shapes, right? So that I point to 3D GAN, which is one of the pioneering works from 2016. So that method combines volumetric CNN and generative adversarial networks. So I wouldn't sort of go into technical details, but I'm going to show you the results of 3D GAN. As you can see, the so-called shapes being generated by 3D GAN are more like voxel clouds, right? So they are not like the coherent 3D shapes. They don't really have clean boundaries, for example. So this sort of begs the question, are voxels a good new representation for 3D shapes? So then what is really a shape? So, actually on several occasions when I was doing my research, when there's a sort of key concept, I actually went back to the dictionary to find, what is correspondence, what is segmentation? And so now the question is, what is a shape? So a shape, by the dictionary definition, is a shape is an external form. Okay, it's the appearance, characteristic of something or someone, and it's defined by the outline of an area or a figure. Okay, so I'm going to highlight these two keywords. It's an external form, and it's the outline of something, right? Now, then the shape really is defined or characterized by its boundary, right, or outline. Well, you say, well, images have boundaries as well, but the image boundary is actually artificial. The images have boundaries only because we have to crop, right? That boundary is always rectangular. So it's a different thing. So now if you admit or agree with me that shape boundary is, shapes are about what the boundary is, then the shape boundary is defined by what's inside and outside, right? So this is inside, that's outside. And it's not about feature aggregation in these preset boxes, which you would use for a classical CNN, right? And this feature aggregation in these preset boxes are actually about texture inference, right? So I see there's a distinction. So in fact, people have noticed that this is a recent paper that essentially says that when you look at, say, if you look at the image in C, that humans actually tend to see a shape. There's a cat there. On the other hand, if it's a CNN, and CNN is actually
we just lost your audio for a bit, Richard.
Okay, now can you hear me now?
You're back. Now you're back. Yep.
Okay. So yeah, there's a bit of instability. So let me sort of repeat. So the point I want to make here is that there has been a recent study that show that humans tend to see shape, especially if you look at the image on the right, that people see that there's a cat in there. But if you use a CNN to do discrimination or classification, so it will actually classify that as an elephant due to the texture, because I believe that CNNs kind of sees texture more so than shapes. So then to learn to generate shapes, we should ask the following question. So I give you a point as, is this point inside or outside the shape? So if that's inside, that's outside, inside, inside, keep doing this exercise, and then you can define the shape, right? So the shape is defined by whatever points that lie inside. And this inside outside would help you define the boundary. So if you take a typical CNN-based shape generator, it would start with some kind of a code. The code could be noise or could be some results of an autoencoding, and then you can apply your favorite deconvolution operator, and at the end you get a result. Now, if you look at this mapping for a particular outcome in the final image, it's a function of image features in some box from the original image, right? And that code is actually the result from some kind of encoding of an input image. So the shapes generated are these voxel distributions, as you can see from 3D again. Now, with this notion of shape being defined by boundaries and boundaries about what's inside outside, let's learn a different mapping, right? So here my function is going to be f, and that's going to be defined by a shape code s and also a particular coordinate p. So here can be just x, y, z of a point in 3D. And then the question is this point p inside or outside of the shape s? You can say it's 1 if p is outside, 0 otherwise. So this actually defines an occupancy. And this is the so-called implicit representation, right? If you've learned this field, then the shape can be extracted by just taking the 0 level set, pretty classical thing in computer graphics. Now, another thing which is really, really important is that using this representation, we're actually learning continuous functions. We're not learning a discrete representation like images of voxels. The point P can be sampled at any resolution, right? So even if your input is 64 cubed, you can actually sample P at a higher resolution. You're going to get whatever result that the sampling resolution is at. And finally, this is called a neural implicit representation. There's another term which is called coordinate-based neural representation. It's actually spatially smooth with respect to the coordinate p because it's explicitly part of the input, and you cannot say the same about the CNN-based decoding. So then this led to this paper called RvNN, which was published in CVPR 2019. It does exactly what I described. So this is a network which is actually a pretty simple one. It takes a shape encoding and takes a point coordinate. And after a bunch of NLPs, it's just going to learn what's inside and what's outside. The way to train this network is to use these point value pairs. And this network actually learns shape boundaries. In contrast, the traditional CNN-based decoders learn feature to voxel mappings, and these features are voxel intensity distributions inside various boxes that you use for your convolution. So here is a very telling toy example to contrast the CNN-based decoding versus RvNN, which is the IM here stands for implicit. So the task here is trying to learn to generate these letter A's treated as a shape. That is, so the letter A here is black and it's on white background. And on top, you see how the network converges to generating an A. And at the bottom, you see for a CNN-based decoder on the top, and at the bottom, I have the RvNN, and it also tries to learn to generate an A. Now, you can see the contrast here is that for the CNN-based decoder, it does this image intensity refinement, right? And clearly, at the bottom, it's doing something different. It's doing shape boundary refinement. And in another exercise, we do interpolation. So here is essentially you have a source and you have a target, and then you learn this latent space and just do a linear interpolating latent space, and you take one of the interpolated code, and then you're just going to generate a result. And you can again see the contrast between a CNN-based decoding for interpolation, where it does this interpolation using by adjusting the image intensities. It does go from this A on the left to the A on the right, but it does so in a kind of an unnatural way, where you actually expect if this A is treated as a shape, the interpolation from the left to the right should be a movement, right? This is actually what the RvNN-based interpolation gives you. It's actually moving the A from the left to the right. So I see these two examples as a clear contrast between what's happening with the CNN-based decoder versus what's happening with the RvNN. And then, of course, this decoder can be plugged into different applications. It can actually can do single view reconstruction. It can do autoencoding. It can also do an IM GAN, where you can actually generate shapes from random noise. And then these are some comparisons, and I highlight in the box. These are results from the IM GAN, which is the generative adversarial network built on the IM decoder. And then in contrast to other risks like 3D GAN and CNN-based GAN, and also point cloud based again, the results, it is visually, IM again comes on top. And you also note that IM again can operate both at a low resolution or high resolution. Actually can be sampled at any resolution as you wish. And then here are some results for interpolation, again, contrasting the other works. There are certainly more details in this paper if you're interested in it. Okay, so we said boxes are bad, right? But these preset boxes are bad. But if the boxes are right, we actually want the network to be able to learn these boxes if the boxes actually represent something which is semantic, which is structural. So shaped parts are the boxes that we want. So after IMNet, what we thought about was would it be possible for something similar to be able to learn structure. So it turns out that the idea can be actually very simple. So this is the original IMNet. It's trained with the reconstruction laws, right? Because it's trained using this point value pair. It just tries to approximate the inside-outside status. Now, all it took was just to add a branching layer, right? So this is exactly the same as IMNet. Now we're just adding a branching layer, which is the last layer before you apply the reconstruction laws. And this branching layer essentially is trying to recover the parts, right? And at the end, we're going to do a max pooling, and the loss is exactly the same as the IMNet. So, and do know that to train this network, we actually don't have any part label as supervision, right? We use exactly the same training as IMNet. And the goal here is actually to learn a segmentation without any part labels to supervise. We call this network BAE-Net, and BAE stands for branched autoencoder. And the way to train this is to train this repeatedly using a set of unlabeled shapes, and that belong to let's say their old chairs, right? So this setting is what is called a co-segmentation. We try to segment a set of shapes altogether. It is unsupervised, and it can also be applied to one-shot learning, where you can provide one a labeled shape. This is the one that you see here in the box, and then this label can be propagated to a very large set of chairs. So the key question is, why does this work, right? Something so simple appended to the IMNet is able to do this unsupervised co-segmentation or one-shot learning. The key here is that we're exploiting the structure of a small implicit field network. Okay, small here can mean two things. The first of all, the network is actually very shallow. Okay, it has only 3 layers. It turns out 3 layers actually works pretty well. We tried, 2 and 4 other layers. 3 layers actually turned out to work pretty well. And also, it's small because it has few neurons. You can see these numbers here. So on top, you have unsupervised learning, the numbers, and at the bottom, you see network capacity for one-shot learning. Here, N stands for whatever number of labels you have in that one or few examples. So with this small network, you're kind of applying some kind of a compaction, right? So the network is forced to find compact. And this compactness seems to actually lead to consistency. And this is certainly not something that's never been discovered before. And it has actually appeared in other settings as well. So there's compactness to this consistency, and the network is able to learn these parts. And this is a tour example where you can see in different branches, the network seems to be able to learn different parts that compose these shapes. Now, we looked into this a bit closely, right? So we looked at the neural activation maps for each layer. We want to see what network actually learned in each layer. It turns out that in layer number 1, this network seems to have learned this linear gradient fields, right? So you can see, right? You see this linear ramp, right? And then in the next layer, you learn something complex, seems to be combining these linear gradient fields and form these shapes, right? And then, of course, in the third layer, it's further combining what's learned in the second layer and to form more complex shapes or configurations. So there's some interpretability in this network, right? That's something we found after the BAE-Net, right? So now, then it's natural to ask question, would it be possible to make this interpretability explicit, right? So we actually explicitly force the first layer of the network to learn planes, okay? We tell it exactly just learn planes, right? And then in the second layer is planes, which will give you these half spaces, and they're gonna be combined to learn convexes, right? So if half spaces convex and their combination, its intersections can become convex shapes. And in the last layer, right, we do a merging. Like this merging actually would put the unions of this convexes together to potentially give you concave shapes, which is more generous. And we don't want this network to only be able to reconstruct or generate convex shapes. So that's kind of the idea for the work that followed BAE-Net. And we call it the BSP-Net, right? So BSP stands for binary space partitioning, which is a very classical thing from computer graphics. And in here, the very first layer is exactly doing the binary space partitioning, right? We're learning these planes, right? And BSP-Net is another neural implicit model. And in fact, its input and output are exactly the same as RvNN with the same reconstruction laws. And what's new here is that the shapes are formed by BSP, right? And of course, different layer does different things. And the planes are actually defined by the learned network weights. And this paper was published in CVPR 2020. So in essence, this network BSP-Net was trained to learn how to best represent a set of training shapes. So maybe this is whatever set of data you can get from, say, ShapeNet, and using a particular number of planes, right? So this number of planes defines network capacity. So maybe it's 4,096 planes. And during inference, these planes and convexes can be easily turned into a output mesh, right? So I'm a graphics person, so graphics people love meshes, and this BSP-Net was one of the first neural network that was trained to generate meshes directly, right? It's not like for RvNN you generate an implicit field, and from the implicit field to the mesh you have to do marching cubes, as you can see from the image on the right, right? You get these small triangles as is typically the result for marching cubes. In contrast, for BSP-Net, because you already have the planes, right, and you can actually directly get a mesh just by using CSD operations, and you can also obtain sharp features, and the meshes obtained can be easily textured. And you also have a more compact representation compared to the results from marching cubes if you do compare the counts of the polygons in these meshes generated. Furthermore, these planes given by the neurons in the first layer actually can be used easily to establish correspondence between the different shapes generated, right? So here you see, in fact, the BSP-Net can be adapted to produce structured single view reconstruction. The top are input images, and at the bottom you have the results. Here, I do want to point out that BSP-Net does not really learn shape semantics. Okay, you have these parts that are colored, seem to be reflecting semantics. It is propagated from one manual labeling, right? Because the planes are naturally corresponding, you just have to provide one label, and this label is propagated to all the other planes that are constructing the shapes. Okay, so now I have a mini summary of neural implicit models. So there's now sort of neural implicit models are being talked about a lot, and at CVPR 2019, amazingly, 3 works concurrently all propose pretty much the same idea, okay, which is to learn continuous functions by either learning occupancy grids or by learning a signed distance functions. You have RvNN, OCCNet, and DeepSDF. And as I argued in my talk, that I believe that implicit functions are more suitable for represent shapes, and also it learns continuous functions rather than discrete grid representations like voxels and images. So since then, only in the past 2 years, there has been a lot of follow-ups on neural implicit representations. There's a very nice I've got a blog or something by Vincent Seisman summarizing the development of neural implicit models. And just to pick a few examples of follow-ups, there have been local models, right, with the challenge, trying to address the challenge of learning more details, right? You can see most of the results produced by BAE-Net are pretty smooth. How do you get topological details, and how do you get surface details? There have been follow-ups on learning more localized models. And we have a recent work on doing a disentangled representation to be able to reconstruct the surface details from images. And another work that is from 3DB 2020, in fact, it's actually the best paper award winner. That was actually really interesting to me because it's actually related to learning interactions. Remember, interactions and functionalities are intricately connected. And in this work, which was called grasping field, the task is actually learning to generate interactions between a human hand and objects. The key thing here is that in order to do that well, you actually need to be able to learn context, right? You need to be more exact about context. And then it's actually all about boundaries. And this is why the implicit representation is perfectly suited for this generative task. And then finally, if you're in graphics and computer vision, you must have heard this paper from 2020, which is called NERV, or Neural Radiance Field. And actually, these implicit neural networks for IMNet, OCC, and DeepSD have turned out to be prelude to NERV. So if you think, so the IMNet and OCCNet, they learn from a mapping from the 3D point coordinate to an occupancy. In contrast, the NERV learns a 5-dimensional function that maps a direction and a point coordinate to color and density, right? And of course, NERV itself has so many variants and follow-ups just in the past year or so, right? So if you're interested in this kind of development, I highly suggest I think we started with a blog by Frank Dellard to have a wonderful account of all this development, very, very recent and intensely active development on NERV and how it's related to this neural implicit models. But there are still things are missing, right? So we're certainly not done yet. So so I'm not going to sort of talk about everything. Again, I suggest you get Vincent Seisman's a page. So one of the questions he highlighted is how to do this direct convolution on these implicit representations. And what I want to point out is that these implicit models are not really designed to learn part relations, which is essential as a structural understanding, and certainly is highly relevant to addressing this functionality challenge, right? Functionality and part relations and structural understanding come hand in hand. So I'm going to switch gear to sort of the second part of my talk, which is on learning structural representations. So I'm going to start by introducing to you a particular structural representation for man-made shapes, which is called a symmetry hierarchy. So symmetry hierarchy uses symmetry to guide the grouping and assembly of shape parts and to form a meaningful hierarchical part organization, as you can see here as an example. So now here is a more sort of a progressive example of a symmetry hierarchy for a chair model. So here we first assume that you already have a part segmentation, and the key is to learn an organization of the parts. So we have symmetries. So we have self-symmetries for each part, if there is one. And also we're going to detect all the reflection symmetries. Here you see the two armrests are symmetric reflexionally, and also all the rotational symmetries. And then there's another relation between the parts, which is connectivity, right? So in this graph, the blue edges provide connectivity relations, and the red edges give you rotational symmetry, and the green edges give you reflectional symmetry. So, and then we're going to perform a bottom-up graph contraction, doing so recursively to obtain a hierarchy, to obtain a tree. Right? There are two operations for this contraction. The first one is grouping by symmetry. It happens to be one of the Gestalt law of grouping. And if two parts are symmetric, they can be grouped into a node. And the second operation is simply assembly by proximity. So if two parts are connected, you can combine them into a node and contract the graph. You can do so recursively. And you're going to get a symmetric hierarchy. So there are some key merits of this particular representation. First of all, it's structural, obviously, it's a hierarchy, and the part relations are given by proximity, which is connectivity, and also symmetry. So symmetry, in fact, is very much related to functionality. So I believe that symmetry is a prerequisite to functionality, right? So if you have, these man-made shapes, there's symmetries everywhere, right? And actually, in fact, if you don't have the symmetry, it actually will not be able to perform its function, right? If the four legs are not symmetric, the chair may not even stand, right? And also the symmetric grouping, which is performed by this hierarchy construction, is related to functional grouping because obviously symmetric parts tend to perform the same function. Another key merit is that this representation is purely structural, right? So it doesn't really care about the fine-grained geometry of each part. It only cares about whether the two parts are connected or they are symmetric, right? So with this representation, we can actually decouple structure and the part geometry, right? The tree is about structure, and the leaf nodes give you the part geometry. So wouldn't it be nice if we're able to have a neural network that is able to learn to generate symmetric hierarchies? And it's a good idea because with this generative model, you can decouple the generation of structure and generation of part geometry, which would actually lead to advantages in the final outcome. So to be able to do that, there is a particular kind of neural network, which is called a recursive neural network, which turns out to be a perfect fit for learning to generate symmetry hierarchies. So a recursive neural network here, I call it RvNN, is a tree structure, right, where each node in the tree is a neural network. So here you see one neural network that takes two n-dimensional vectors to produce another n-dimensional vector, and then you have another sibling network, and then the two outputs can be fed into a neural network. And then actually each one of this neural network is the same, it has the same parameters, right? And the network is trained to perform certain tasks with the same network at each node. Now, to learn symmetry hierarchies using RvNNs, so we're going to represent a shape just by using this box abstractions, right? So each box is encoded as a fixed dimensional vector, and they form the leaves of this tree. And then the question is how then you define the network laws, right? So the first idea is to turn the RvN into a recursive autoencoder, right? So this autoencoder is going to take a box arrangement as input, and the encoder is going to produce a root code with a fixed dimensionality. And then the decoder is going to take that root code and is going to construct a hierarchy. And at the end, we hope that the reconstructed hierarchy is going to approximate the input hierarchy. And the reconstruction loss is just summed over the boxes in terms of their spatial locations. And then this decoder can be further refined into a generative model. So all you need is a way to generate plausible code, right? For example, if you want to generate chair structures, you just have to make sure that you have a way to generate these root codes, which can model the, say, the manifold of the set of chairs. And then you just feed that to the decoder, and then you're able to generate the chair structures. That's exactly what we did. So we changed the autoencoder loss to a GAN loss, and to learn a manifold of plausible codes for a particular category. So this allows the network using a BAE GAN to generate chair structures or airplane structures or structures of whatever category you wish. And then finally, in order to get a final 3D shape, this is where the decoupling comes in. The part geometries were generated using a separate neural network, right? So we purposely decouple the generation of structures of the shapes and the part geometries, okay? And to sort of put everything together, all you have to do is to sample a root code, and that's going to generate the symmetry hierarchy, and then you're going to have a separate neural network to fill in the part geometry. And here are some results for this network. We call it GRASS, which is a generative autoencoder for shape structures. And it was at the time, this was from CGraph 2017. It was the first neural network to learn multi-attribute structural graphs. And it's able to provide a coarse to fine synthesis, structure first, and then geometry. You can get high resolution compared to result, clean parts, and with structure compared to earlier work such as 3D GAN. And after that, we extended this RvNN to indoor scenes, right, where the components are going to be 3D objects, and they have these relations that can be learned and to be applied in this RvNN framework to generate indoor scene layouts as the ones that you see here in this image. And all of these scenes were generated from random vectors in a very short time, fractions of a second. So you're actually able to generate a lot of indoor scene layouts. Okay, so to summarize sort of this part, which is the learning structures, there have been other follow-ups since GRASS, which was from 2017. So one line of work is try to do a single view structure recovery from CVPR 2018. And also there's an extension to hierarchical graphs, not just trees, by StructureNet. And there have been other structural generative models for 3D shapes. I'm just going to point out a few of them: CompoNet, SecNet, and SCMNet. So it's important to know that actually for all of them, there was this decoupling between structure generation and geometry generation. So maybe in retrospect, I feel perhaps the part geometry really ought to have been learned using implicit models, because that actually provides you with visually high quality geometry. But the implicit models are not by design structure aware. So what's next? So first thing I think that's really interesting is actually to remove the supervision. Is it possible to learn 3D generative models without 3D supervision? Right. So although if you think of BAE-Net, it's kind of unsupervised that there's no part labeling, but we still need 3D shapes to supervise IMNet, BSBNet, and other things. So is it possible to do single view 3D reconstruction or structure recovery without 3D supervision? Is it possible to do structure geometry disentanglement again without supervision? So I believe the key is to find the right inductive bias. So symmetry could be a good candidate, and part priors, which is, for example, convexity or simplicity or compactness, and also potentially compactness of the structure, right? Would it be possible to define a network loss that is on the number of operations in a tree? I think that's actually a very interesting question. That is something that we're investigating, how to make that work and still have a differentiable loss. And another line of work is to do unpaired shape transform, which is like a cycle GAN for 3D shapes. So we had some preliminary results along those lines. And also going beyond geometry. As I mentioned, that the reason we generate 3D shapes is to use them in real life, right? To be able to use them, you want them to have good affordance. You want them to function. And if you want to produce them physically, you actually want them to have structural integrity, to have manufacturability, right? I think all of these criteria are the ones that really haven't been studied much at all in the development of 3D generative models. So this work, which I'm showing over here, has nothing to do with deep learning, but it was the first attempt to generate furnitures that are functional using some kind of evolution and remodeling, but to define a neural model for generating things which are functional, can be manufactured. All these things I think are open questions. And finally, I'll go back to this original point that I tried to make, that I believe that learning to generate is at the heart of AI. So it is something I'm personally very interested in, and many other people are interested in. And there's actually a subfield which is called computational creativity. And there the very goal is to try to develop a machine or some kind of computational model that can lead you to something which is creative. So it's a very challenging problem. I certainly encourage that many people are going to start looking into this. It's not a field that has been studied that much in machine learning yet. There have been some attempts. I'm a believer that it may actually be possible. You know, Ada Lovelace didn't believe it was possible. That's why this test was attributed to her. There was this very interesting quote from a guy who's not a scientist, it's actually an actor. It says, creativity isn't a talent, it's a way of operating. If you believe in that, then maybe creative modeling can be operationalized. All right, so that's all. Here are the works that were covered. And I want to also thank my students and many collaborators on these works. And with that, thank you very much.
Great, thank you. Yeah, I know, excellent talk. So many interesting discussion points. Let me, while people post some questions on chat, let me get things launched, because yeah, I have a big list of questions and things I'm curious about. So, yeah, one was for the implicit models of surfaces. Isn't that problematic for really thin surfaces at some point? So, and that's one question. And then another question is, to what extent are these models orientation invariant, or are they and scale invariant versus targeting some canonical orientation and scale?
Okay, so let me answer the first question. So, so indeed, the original works did have trouble with thin structures. And then, of course, then there's more localized models are, so essentially, instead of having just a code for the global features, you can also have, you can also encode more local features, right? And then feed that into the implicit neural network, and then it's able to do a better job in terms of reconstructing thin structures. So one paper I want to point out is something called a DISN. I actually forgot what it stands for. It's from Adobe. So it uses local features to be able to do a better job in terms of reconstructing topological structures. So our work, which is it still hasn't been published yet, went one step further and trying to recover surface details. It's actually different kind of details, not the thin structures, topological details, but surface structures. Can I hear the second? So first of all, I hope that answers.
Oh yeah, no, that's good.
So what's the second question?
Oh, the second one question was about orientation invariance and scale invariance, and whether for some of these models are they being trained according to certain canonical orientations, or in the end do they work for any orientation and scale?
I think, well, I don't think we have rotation invariance. So okay, these are all models that are uprighted already. Yeah.
Great. Okay. So you know, I don't see any questions yet. Let me again encourage you to, or actually, I'm not looking for. I should look for hands up as well. Don't see any hands up. So I'm going to keep on going with my list of questions, because I've got lots of them.
Can I ask a question?
Oh, absolutely. Yeah, I didn't see your hand. Yeah, go for it.
So I'm kind of curious. So I'm guessing, kind of related to what Michael said, is you do have a grid underneath all of those, right? Even under the BSP, I guess you have an underlying grid, or you have some finite set of planes. Like, where is what's the discretization basically underneath those?
Yeah, so the number of planes predetermined.
Okay.
So for example, all the results you saw are ones using 4,096 planes.
Mm-hmm.
Yeah. So, but there's no sort of a like a voxel grid, but the number of planes that defines the network capacity.
Okay,
and let's say the RvNN or the graph or the other ones, you have kind of related to the fact that you said that you are training on an upright orientation. So there's also a grid orientation, I'm assuming, right? So the grid is, let's say, front facing, where you have some notion of a front.
Yes, I believe the shapes are aligned, yes.
Okay. So I'm just wondering if you had any thoughts about how to get away from that?
So my simple answer is that it's easy to align them. So that's why everyone is using it, right? So
it's easy to align in the coordinate system, not in the system in which you scan, right? I mean, if you are scanning, if you're taking a photograph of an object, that can be arbitrary, right? I mean, yes, maybe your object, your training data is probably aligned.
Yeah.
But your actual kind of capture inputs are not, right? I'm just wondering about the discrepancy and if you have any thoughts.
Yeah, I think this rotational invariance, I think it's actually pretty tricky. So I mean, maybe what I'm going to say is it's not really related to an answer. We actually tried to train. So we had a recent paper which is called a gun hopper. It's like a cycle gun, but we do this like step by step. So we actually tried to train the network to rotate like a bar, right? And that turned to be actually very challenging. The network doesn't actually seem to know that this rotation. It tries to just do the kind of a CNN kind of a thing. So yeah, to maybe give you a short answer, no, I don't have a clear intuition as how to deal with rotation.
Thanks. I was curious.
Great. Let me ask a question about using procedural models to produce augmented data sets. And so is that, how feasible of a path is that to, because in many cases, you know, data augmentation is as much of a key to anything else for training many learning-based methods. And so are people in this domain making full use of kind of relatively sophisticated procedural modeling and seeing if they can invert those, et cetera?
So indeed, if you look at the work that I mentioned, which is the one using RvNNs to generate indoor scene layouts, that paper, I think the main use was actually data augmentation. Because although, I mean, I just showed you the results very fast, but if you actually look closely, everything has something which is not right. So it's kind of a rough thing, right? So they are indeed, I think the best application is actually data augmentation, because you can so easily generate so many things which are plausible to some extent, but they're not like production quality. So this also maybe goes to one of my main points. I think there's still so much more in terms of generating things which are actually usable, which are actually functional. So indeed, I would say to be able to generate lots of 3D models as a way to augment data, maybe right now the best application, right? So there's this notion of saying that one picture is worth 1,000 words, but one 3D model is like 1,000 pictures, right? It's like a lot of people already use this to generate one 3D model and take multi-view images. You can use the images to actually train, image analysis or image generation algorithms. So yeah, so indeed, very much is in play.
Yeah. Okay, great. I'll ask one more question. I don't see any other ones up right now. Can methods do better at leveraging, at both estimating and then leveraging surface normals as a core part of what they're, of the representation? Because I guess, the surface normals are implicit in the implicit representation, but how about, are there methods that make strong explicit use of surface normals?
So yeah, so this works that I mentioned, as far as I recall, don't use surface normals. But if you have reliable surface normals, it can be very useful to be able to generate. So we actually have a recent project which is still ongoing, trying to make the ICCB deadline, is to do reconstruction of these like cat-like objects, like then if you're familiar with ABC data set, right? We try to use that. And actually the ABC data set is very challenging because it doesn't have a lot of like in-class consistency. These are all these machine parts. So our goal is actually to be able to generate high quality CAD models, right? With good sharp features and also with a small number of primitives. It turns out that we couldn't really develop a network which can really generalize very well. So we can do a pre-trained network, and then we do fine-tuning. And in that fine-tuning, it turns out normals actually can play a very key role to actually generate this high-quality CAD model. So indeed, if you have accurate normals, for sure it's going to be useful, right? You can also argue that with normals, inside-outside is given, right? So, so this is why it doesn't make sense for RvNN to actually use normals. But if you want to generate high quality, for graphics people, CAD models, I think normals can be very, very important and useful.
Great. Oh, we do have one question in chat from Yulang Xu, who asks, the choice of sampling strategy will affect the implicit function learning. Do you have some ideas about the sampling strategy?
So we have some details in IM. We don't sample everywhere. We sample near the surfaces. So I'm not sure if that answers your question.
But yeah, is that a stochastic process, or it's structured in some deterministic way, or
in terms of training, or in terms of like?
I think the question might be for training, but yeah. So
we sample points which are near the surfaces, because the training shapes are there, right? So we use this, yeah, they're in a supervised, in the sense that you need to know what is the target surface to give you the inside outside. So in that sense, we only sample near the input the training shapes, surface of the training shapes.
Yep, got it. Let's see, a call to the audience. Other questions? Keeping an eye out for hands up, etc. Let's see. And yeah, let's see. Let me ask another kind of question. So yeah, the Vincent Sitzman work, I guess, using the periodic activation functions. Can you explain why that works, or does that make any sense? Or yeah, anyhow.
So I have to say I haven't read that paper carefully, but I think the paper, the focus there is to be able to generate high frequency details, right? So and actually, so this is, I think, is representative of a line of work that I call them like they're overfit, right? So the network is trained to reconstruct, for one data set, one input shape really well, right? So in a sense, if you look at sort of a generative model, so there on one hand you have this sort of overfit network that gets really high quality reconstruction. On the other hand, you have RvNN, OCCNet, they're trying to generalize, right? So the periodic activation function, I think, is essential to generate high frequency details that are not possible using. For example, what we use is rectified linear activation functions for RvNN.
Yeah. Okay, great. Let's see. Yeah, okay. Let's see. Satara, did you want to ask your question? Or else I can ask it for you. Up to you.
Yeah, so I'm not sure if we talked about this or not. I'm not sure if I catch this, but my question is it possible to include other attributes than inside and outside in IMNet decoder? So we could, for example, have colors included.
Oh, sure, absolutely. So that's what NERF is, really, if you will.
Oh, okay.
Right? So for example, deep SDF learns sign distance, right? That's what SDF is, right? And then certainly you can, any other attributes you can think of, right? So the here is the mapping is a NERF is from two angles which defines the orientation, and then the point coordinate, right? And that gives you color and intensity. So that's a classical example of extending inside outside to other attributes.
Thank you.
Yeah, and also you can extend these implicit models by looking at what is the primitive, right? The primitive could be just points. It could be other primitives. You can think of, no primitives that people using like balls, spheres, right? And you can think of that for BSP-Net, the primitives are planes. So I think I think what's cool about it is something really simple, right? Simple actually makes it highly extendable, right? You can think of all kinds of ideas to play around with it. Yeah, so hopefully there can be many more follow-ups along those lines.
I'll ask maybe a wrap-up question. So there's so much depends on the choice of representation and what's a better representation to work with, and maybe ideally, of course, the representation should be learned, and But so in terms of if we're on a spectrum from, okay, we really don't know what the best representation is at one end of the spectrum to at the other end of the spectrum, you know, maybe you could argue, okay, we have enough representations and we just need some hybrid representation or and ways to convert between existing representations. Yeah, and then, you know, are the best forms of representation still to be learned, or how far along that path are we?
I mean, I think it's a very large question, because, you know, I don't think that you can actually define what the best representation is, right? There's always, you know, what's your application and what's your task. And sometimes, you know, there's no reason why, you know, that, you know, gridded pixel represent is the best representation. It just turns out to be the representation that fits the best with convolution, right? So sometimes it's because what operation you want to perform, right? For certain representations, it's easy to define certain operations, right? But then, you know, then you can just pick any representation like meshes, right? And people try to define mesh CNN, they try to define convolution on it. So I don't think there's a unique answer to what the best representation is. And of course, the implicit representation came along and it seemed to be very popular because they are able to produce really high quality results because of the continuous nature, and because that is just really fit, because they started with the shapes now, right? People that generate, try to use continuity as the other criteria that makes it work. So maybe just, I don't think there is a representation even for 3D. I'm happy to see that there are so many representations that are possible, because it just means there's so many papers people can write, right? So, yeah, I mean, can you actually learn what the best representation is? That'd be fantastic if that's possible.
Oh, sorry. I just wanted to say, yeah, let's wrap up there so that people can go on to the next meetings, etc. But I hugely appreciate you taking the time to come and give this presentation. Super interesting work, and yeah, an exciting future ahead.
Okay, thank you, Michael. Thank you, everyone, for
Thanks,
coming.
Richard. Yeah, thank you.
And yeah, take care.